What if, one ordinary morning, the sun simply vanished from the sky and something else took its place? Not a metaphor, not a thought experiment confined to a chalkboard, but a real physical swap. Our familiar yellow star pulled out of the solar system's center and replaced with something else entirely. A cold, dim ember. A monstrous, swollen giant. A point of near infinite density that bends light itself. What would Earth's sky look like in the seconds, days, and years that followed? Would we even survive long enough to notice the view? This is the story of what happens when you take the one constant of our existence, the sun, and swap it for some of the strangest objects in the known universe. Before diving into the swaps themselves, it helps to remember just how ordinary our sun actually is. It is a yellow dwarf star, a G-type main sequence star, about 1.4 million kilometers across, with a surface temperature of roughly 500 degrees Celsius. It has been fusing hydrogen into helium in its core for about 4.6 billion years, releasing energy that takes an average of 8 minutes to reach Earth 150 million kilometers away. In the grand cosmic census of stars, our sun is bigger and brighter than roughly 85% of all stars in the galaxy, most of which are small, cool red dwarfs. So even before we start swapping it out for exotic monsters, it's worth appreciating that the sun itself sits in something of a Goldilocks zone of stellar properties. Not too big, not too small, stable, long-lived, and quietly perfect for hosting a system of planets that could eventually produce something like us. Let's start with the gentlest swap, replacing the sun with a red dwarf, the most common type of star in the universe. Something like Proxima Centauri, our nearest stellar neighbor, would work as an example. Red dwarfs are small. Proxima Centauri is only about 1/7 the diameter of the sun, not much bigger than Jupiter, and they are cool, glowing a dim reddish orange rather than blinding yellow-white. If you swap the sun for a red dwarf of similar mass to Proxima Centauri, the immediate effect would be catastrophic for life as we know it. Because red dwarfs are so much fainter, Earth would receive only a tiny fraction of the sunlight it currently does. Within moments, the sky would darken into a perpetual dim, ruddy twilight. Global temperatures would plummet. The oceans would begin freezing over in a matter of years, not centuries. Photosynthesis, which depends on specific wavelengths of visible light, would struggle to function under the redder, weaker light output of such a star, and plant life across the globe would begin dying off in a slow, creeping ecological collapse. Ironically, red dwarfs are also the most common star type, precisely because they burn so slowly and efficiently. Some are expected to shine for trillions of years, far outliving the sun and even the current age of the universe itself. Planets that orbit red dwarfs closely enough to stay warm, however, face another problem entirely. Young red dwarfs are prone to violent flares, blasting out radiation that could strip away a planet's atmosphere over time. So while a red dwarf swap would mean a much colder, dimmer solar system, it would also mean, at least theoretically, a star that could keep burning long after our actual sun has died. Now flip to the opposite extreme. Swap the sun for a blue giant or blue hypergiant, one of the hottest, most massive, most luminous types of stars known. A star like the pistol. Star, located near the center of the Milky Way, radiates roughly 3.3 million times the luminosity of our sun, according to studies of the region, despite having only a few dozen times the sun's mass and a radius somewhere around 435 times solar. Or consider R136A1, a blue star in the Tarantula Nebula that remains, by most, current estimates, the most massive star known, weighing in at somewhere over 100 solar masses and pouring out light and stellar wind at a ferocious rate. If you replace the sun with something like this, Earth would not freeze. It would be obliterated, essentially instantly. The sheer luminosity of a blue hypergiant would flash boil the oceans and scorch the surface within seconds of the swap, long before any slower orbital effects could even register. These stars burn incredibly hot, often exceeding 20,000 to 30,000 degrees Celsius at their surface, compared to the sun's comparatively gentle 5,500. They also live extraordinarily short lives, burning through their nuclear fuels in only a few million years, a cosmic eye blink compared to the sun's multi-billion-year lifespan, before ending in a supernova. So this swap wouldn't just be lethal, it would be a preview of an ending. Blue giants are essentially stars living fast and dying young, and swapping one in for the sun would mean trading 4.5 billion more years of stability for a blinding, brief, and ultimately explosive future. Next, imagine swapping the sun for a red giant, essentially a preview of what our own sun will eventually become in roughly 5 billion years, once it exhausts the hydrogen fuel in its core. As stars like the Sun age, they swell dramatically, their outer layers puffing outward while cooling to a reddish hue, even as their total energy output increases. A red giant like Aldebaran, with a radius around 44 times that of the Sun, would already extend far beyond Mercury's orbit if placed at the solar system's center. Mercury would almost certainly be engulfed. Venus's fate becomes trickier and more debated, but in many models, Venus is swallowed too. Earth's outcome is genuinely uncertain in the far future. Some models suggesting it could be consumed by our Sun's own red giant phase, others suggesting it might survive, but be scorched into a lifeless, baked husk as the expanding star's outer atmosphere brushes past. Swapping in a red giant now would compress this slow-motion 5 billion year process into an instant apocalypse. The literal photosphere of the star, its visible surface, would swallow the inner planets outright, while Earth, depending on the exact size of the giant chosen, might find itself either inside the star's tenuous outer atmosphere or just barely outside it, broiled by radiation regardless. But if you want real astronomical extremity, you go looking for the largest stars ever measured. Names like UY Scuti and Stephenson 218 get thrown around online as the biggest star in the universe, and it's worth being honest about how uncertain and frequently revised these measurements actually are. For years, UY Scuti was cited as having a radius roughly 1,700 times that of the Sun, but more recent distance measurements from missions like Gaia have repeatedly revised that figure downward, with current estimates placing it closer to somewhere between 750 and 1,100 solar radii. Still almost unfathomably huge, but smaller than once believed. Stephenson 2218, a red supergiant sitting roughly 19,000 light-years away in the constellation Scutum, has been estimated at around 2,150 solar radii, although astronomers are candid that this figure sits right at, or even beyond, the theoretical size limit that current models of stellar physics predict a star can reach before becoming gravitationally unstable. If a star like this replaced the Sun, its outer surface would swallow not just Earth, not just Mars, not just Jupiter, but would extend out toward, or even past, the orbit of Saturn. The entire inner solar system, everything we consider home, would simply exist inside the tenuous, gaseous body of the star itself. And yet, remarkably, these hypergiants are not especially dense. Their mass is often only a few dozen times that of the Sun, meaning their outer layers are extraordinarily thin and diffuse, more like a very hot, glowing fog stretched across billions of kilometers than a solid ball. It's a strange contradiction. An object vast enough to contain the orbits of half the solar system. Yet if you could somehow weigh it against its volume, it would be almost ghostly by comparison to something like Earth. Now for the swaps that stop being about size and start being about the death of stars altogether, picture the Sun replaced by a white dwarf, the compact burnt-out core left behind after a Sun-like star sheds its outer layers at the end of its life. A white dwarf might have roughly the mass of the Sun packed into a sphere only about the size of Earth, a genuinely staggering degree of compression, and it emits light not through active fusion, but simply through residual heat, slowly cooling over unimaginable stretches of time. If the Sun were replaced with a typical white dwarf, Earth would once again face a freezing, starving darkness because, although white dwarfs can initially be quite hot, their small size means they radiate far less total light and heat than a full-sized star. A white dwarf swap would represent, more than anything else, seeing what our own solar system might eventually look like billions of years from now, after the Sun has already burned through its life, expanded into a red giant, shed its atmosphere as a planetary nebula, and settled into the slow, cold retirement that most stars like it are destined for. But go even further down the compression scale, and you reach neutron stars, arguably one of the strangest objects that still deserves to be called a star at all. A neutron star is the collapsed core of a much more massive star that has gone supernova, and the numbers involved are almost impossible to hold in your head. A typical neutron star packs somewhere around 1.4 times the mass of the Sun into a sphere only about 20 kilometers across, roughly the size of a city. The density that results is so extreme that, according to NASA and multiple independent estimates, a single teaspoon of neutron star material would weigh somewhere in the range of 1 billion tons, more than the combined mass of every human being currently alive on Earth. If you replace the Sun with a neutron star, the star itself would essentially vanish from the sky as a visible disk. It would become a barely perceptible point, and Earth would be plunged into darkness and cold within moments, since a neutron star's tiny surface area, despite scorching internal temperatures, radiates a vastly smaller total amount of energy than the Sun's enormous surface. But the light problem would be the least of anyone's worries. The sudden replacement of the Sun's gentle gravitational pull with the gravity of an object with comparable mass concentrated into a city-sized sphere would, at Earth's actual orbital distance, technically leave the overall orbital mechanics of the solar system's planets largely unchanged, at least in the immediate aftermath, since gravity depends on mass and distance, not the physical size of the object producing it. In other words, the terrifying part of a neutron star swap isn't really about Earth being torn apart by tidal forces from a safe orbital distance. It's about losing virtually all warmth and light in an instant, an existential darkness rather than a violent shredding. And then, at the absolute frontier of stellar evolution, we arrive at black holes. This is where things become genuinely mind-bending, because a black hole swap forces us to separate two things that intuition usually links together: mass and visible size. If you swap the sun for a stellar mass black hole of roughly the same mass as the sun, a hypothetical object, rather than something observed in nature, since black holes this small are thought to require even more mass to form. The astonishing thing is that Earth's orbit would barely change at all. Gravity at a fixed distance depends only on mass, not on how that mass is arranged in space, so a black hole with the sun's mass would keep Earth in essentially its current orbit. What would change catastrophically is everything else. No more sunlight, no more warmth. The sky reduced to true, permanent blackness, except for the faint light of stars, and perhaps a warped, distorted ring of background starlight bent around the black hole's event horizon by its immense gravity, an effect called gravitational lensing. Earth would become a dark, frozen world drifting in silent orbit around an invisible gravitational well, its presence betrayed only by the way it bends the light of everything behind it. Push the concept even further, and you can imagine swapping the sun for the supermassive black hole that actually sits at the center of our own galaxy, Sagittarius A Large. Astronomers directly imaged this object for the first time using the Event Horizon Telescope, releasing the now famous image in 2022 and refining it further in subsequent years with new polarized light data revealing spiraling magnetic fields around its edge. Sagittarius A Ars has a mass of roughly 4 million times that of our Sun, all concentrated into a region whose event horizon, if placed at the Sun's location, would only be around 12 million kilometers across. Smaller than Mercury's orbit, but with 4 million times the gravitational pull. A swap like this wouldn't just kill life on Earth, it would completely rewrite the architecture of the solar system. With 4 million times the mass at the center, every planet's orbital period would shrink dramatically, since orbital speed depends on the central mass. Planets would go screaming around their new gravitational anchor in wildly shortened years, assuming they weren't first torn apart by the immense tidal forces or gravitationally flung outward in the initial gravitational shock of the swap. And yet, remarkably, Sagittarius A is considered a relatively quiet supermassive black hole compared to many others in the universe. It isn't actively feasting on huge amounts of surrounding gas and dust, which is part of why it appears comparatively dim for something so massive. Finally, for the sake of true cosmic perspective, consider the ultimate extreme, swapping the Sun for TON 618, one of the most massive black holes ever measured, located billions of light years away. Estimates of its mass have varied over the years as measurement techniques have improved, with some studies placing it as high as 66 billions. Solar masses, in more recent analyses, using different spectral line measurements, suggesting a somewhat lower but still almost incomprehensible figure of around 40 billion solar masses. Either number describes an object more massive than the combined mass of a meaningful fraction of all the stars in our entire galaxy, concentrated into a single black hole. Its event horizon alone, astronomers estimate, would stretch across roughly 1/300 astronomical units, meaning if you swapped it in for the Sun, its surface would swallow not just Earth, not just Neptune, but a region of space roughly 30 to 40 times wider than our entire solar system as we currently define it. There would be no solar system left to speak of in any meaningful sense. Planets, asteroids, even the distant icy bodies of the Oort cloud would simply become part of the object itself, crossing the event horizon into a region of space-time from which literally nothing, not even light, can escape. Standing back from all of these hypothetical swaps, a strange and humbling picture emerges. Our Sun occupies an almost impossibly narrow, precise niche among the possibilities the universe offers. Not so small and dim that its planets freeze in permanent twilight, not so large and violent that it incinerates everything nearby within a few million years, not so compact and strange that it collapses the very geometry of its own solar system. It is, in the truest sense, a Goldilocks star, ordinary by galactic standards, yet perfectly tuned to the kind of slow, patient chemistry that eventually produces oceans, atmospheres, and living things capable of asking these very questions. Every one of these swaps, from the faint red dwarf to the ultramassive black hole, isn't really about destruction for its own sake. It's a way of tracing the outer boundaries of what makes a star livable at all, and realizing just how much of our existence rests on one quiet yellow star burning. Steadily, exactly as it has for 4.5 billion years, and exactly as it will for roughly 5 billion more, before its own transformation begins the cycle again.